Hi everyone, we're going to begin the keynote for today. Hope you had a good night yesterday and enjoyed the first day of the conference. So now we'll carry on to begin the second day, and we'll begin with a great keynote from Professor Kevin Zollman. So Professor Kevin Zollman is Herbert A. Simon Professor of Philosophy and Director of the Institute of Complex Social Dynamics at Carnegie Mellon University. His research focuses on mathematical and computational modeling of social behavior. This work deepens our understanding of complex social behavior across multiple disciplines, including philosophy, biology, economics, cognitive science, and computer science. His research answers questions such as how groups learn about the world, how animals communicate, how social norms evolve, how science progresses, and how rationality and morality intersect. That's basically everything. Right? So, without further ado, let us welcome Professor Kevin Zollman.
Okay. Thank you all for coming, and thank you very much to the organizers for what so far has been a really enjoyable and informative conference. And congratulations to the APSA for the first ever APSA. I was really actually quite honored and touched to be invited to be a keynote here, and I hope that in 30 years I can bore graduate students by telling them that I was at the first APSA. You can do it too. So today I'm going to talk about some newish work. It's part of a book that have been promising for forever, but really am about to deliver. But also that connects with some old work that I've done with collaborators Connor Mayo Wilson and David Danks. And I'm going to try and weave together kind of two different themes. One is this question of whether or not science can be progressive because its individual practitioners are irrational, which is an old idea in philosophy of science. And I'm going to tackle it using computational methods. And so I'm also going to, along the way, make some methodological comments about computational philosophy, why I think it's useful, when I think it's useful, and what I think is interesting about it. I'm sort of trying to take a page out of the book of my advisor, Brian Skirms, who told me, you know, don't just tell people how to do things better, do it better, and be an example rather than just a critic. So hopefully I can say why I think computational philosophy is good, but also show you why it's good by answering an interesting question with it. So let me start and just talk about what this thing, the independence thesis, is. And I think this will be familiar to you. So we as a society are very interested right now in social epistemic pathologies. Things like polarization, fake news, misinformation, economic bubbles, groupthink. These are things which are becoming part of our everyday parlance and are something which are of significant interest in the social sciences and in philosophy as well. At the same time, we're identifying a collection of individual biases and heuristics and irrationalities that plague our reasoning processes. And so here is a sampling of 4 sort of semi-popular books looking at these problems. But I mean, I could have chosen any of hundreds of works looking at this. These two sort of parallel research programs are oftentimes thought of as complementary or maybe even potentially the same research program by a lot of people. So they think that the social epistemic pathologies are caused by individual irrationality, biases, and heuristics. And that if we were to make people better reasoners, that we could potentially solve our social problems. So if we got rid of confirmation bias, that would reduce polarization or something like that. And the idea is that this establishes a kind of tight connection between, on the one hand, the group pathologies, and on the other hand, the individual rationality or irrationality of the agents in the community. What we suggested when we first talked about the independence thesis in this paper here was the idea that actually these two different things might be more different than people have given it credit for. And put sort of loosely, the idea of the independence thesis is that the standards of individual rationality might, at least sometimes, come into conflict with the standards of group rationality. So it might be the case that individually rational people could nonetheless have pathological groups, or that individually irrational people might nonetheless make for epistemically very productive groups. And so there might be a kind of robust inconsistency between the two. In this paper, we identified it by an example. So we had a formal example, which was based on a particular statistical model where we showed that it was possible for a good group to be made up of irrational individuals, and that it was possible for rational individuals to make bad groups. And so we showed that logically these two different notions could come apart in that particular example. The idea that these two things might come apart is actually quite old in philosophy of science. So going back to the 1980s and 1990s, a period sometimes called the Science Wars, you had this conflict between sociologists of science and philosophers of science. Sociologists of science identified all of these ways that individual scientists were behaving irrationally, or at least not up to the ideals that philosophers had normally characterized for them. So things like cared about their career, trying to exert their social power in order to get their ideas accepted, trying to subvert their opponents by delaying peer review, or any of a huge number of other things, were all regarded as evidence of the irrationality of individual scientists. They were doing things that were not truth-driven. So they might have been economically rational potentially, but they weren't epistemically rational. And the conclusion that a lot of those sociologists of science, people like Latour and others, drew was that science as a whole must be irrational because the individual scientists were themselves irrational. So this was the sort of anti-science movement of the 1980s and 90s. Now, this is a very different anti-science movement than the anti-science movement we see today. It was an intellectual anti-science movement as opposed to a more political anti-science movement. So Latour has sort of, you know, not quite reneged, but taken a step back from his more strong positions because he doesn't want to be associated with the anti-science movement of the far right, for instance. But nonetheless, it was a different sort of anti-science movement as well. I think a lot of the philosophers at the time who were responding to this, people like David Hall, Miriam Zollman, who Katerina mentioned, Philip Kitcher, pointed out that these two things don't necessarily have to go hand in hand. And they did it by appealing to what I would now call a version of the independence thesis. That is, that they argued that it might be that science is collectively progressive despite, or maybe even because of, the individual irrationality of the scientists. Right? And David Hall, I think, put it most poetically, if nothing else, in this quote from his book, Science as a Process. So he says, in the preface to the book, "I argue for an even stronger thesis. Some of the behavior that appears to be most improper actually facilitates the manifest goals of science. Although objective knowledge through bias and commitment sounds as paradoxical as bombs for peace, I agree that the existence and ultimate rationality of science can be explained in terms of bias, jealousy, and irrationality." So this is an extremely strong version of the independence thesis. Not only is science progressive despite the irrationality of the scientists, but actually it's progressive because of the irrationality of the scientists. That is, it's better off for having individually irrational scientists. And so this was Hull, Zollman doesn't quite go as far, Kitcher doesn't quite go as far, but they're all in the sort of same boat in sort of arguing that the sociologists of science are making a mistake because something like the independence thesis might be true. The central argument, now I'm lumping a bunch of them together, and there are details that are worth exploring here. So if this is an area that's of interest to you, don't just take this as exact description of all of their views, but at a first approximation, the idea is that theories develop over time, and that evidence can initially suggest against a theory and causes premature abandonment. So for instance, Miriam Zollman in her 1992 paper uses plate tectonics as an example. David Hall uses systematics in biology as another example, and Philip Kitcher uses DNA and the different methods in the discovery of the structure of DNA as an example. But in all three of them, they kind of make the same point. Evidence can initially suggest against a theory, causes premature abandonment, but if individuals are irrational, they might ignore that evidence and nonetheless continue to pursue the theory, allowing it to develop over time and eventually win out. So this is sort of the reoccurring, argumentative structure that we find in Hall, in Zollman, and in Kitcher. Now, how can we make an argument for this, for the independence thesis more broadly? So Hull did it via historical case study. Right? So he looked at systematics in biology. The book, which is a very big book, goes into an enormous amount of detail about the sociological relationships between various actors at the sort of important transitionary moment for systematics in biology, and argues that in that moment, the biases and irrationality happened. Miriam Zollman, in her 1992 paper, does the same, but with plate tectonics and continental drift. We could also do it with natural data, potentially, right? We could look at different aspects of science or different scientific fields and sort of try and measure how irrational individuals are or something like that. This, of course, is quite tricky because science doesn't vary that much and we don't have a lot of variation to take advantage of, but in theory, we could potentially do this. Lab experiments would be another way to do it. This is how a psychologist or a social psychologist or a behavioral economist would approach it. They would put subjects in labs, they would measure their rationality or induce them to behave irrationally, and then see if the groups are better or worse in laboratory experiments. And no surprise to you, given the title of the talk and who I am, I'm going to pursue mathematical and computational models as yet another way of studying it. But I do want to emphasize that although I'm going to pursue that latter, it's not that I think that it's the uniquely correct way to approach this, but rather the different methods and models can be complementary, and we can study the same question from various different guises. However, for this topic in particular, I hope what I'll show you is that computational models are really a necessary component of studying the independence thesis, and I hope I'll make clear why toward the end. Now, let me, since I'm going to use mathematical and computational models, let me take a moment to say what data is useful for and what it isn't. One of the ways that I often put this is data is incredibly helpful at telling us where we are. It's incredibly useful in determining whether there is a social pathology or not, what kind of biases at the individual level are present or absent, how we should detect them, how we might be able to detect them, whether they're correlated between individuals in different social circumstances. But what data is not particularly good at doing is telling us where we might be. What would it be like if things were different, if science were different, or if the scientists participating were different? So while somebody like Hall and Zollman can look at a historical example and say, in this historical example, that person was irrational, and also that irrationality led to success for that particular episode of science, we don't know whether we would have succeeded without their irrationality. We can't talk about a law-like relationship here because we don't have the historical data. We can't rerun the tape, so to speak, on the history of science. And so these are the kinds of problems that I think are complementary, where these methods are complementary. That data is helpful in understanding how science is, but modeling can be helpful in understanding what's the relationship between the various things we observe in the history of science. Okay, so let me dive into a particular computational model of cognitive diversity so that we can investigate whether Hall and Zollman and Kitcher's claims about the value of irrationality hold true in that particular model. Okay, and the model I'm going to use is called the bandit problem model, which is one that I've used for a long time. It's used a lot in philosophy and also in statistics. The reason it's called a bandit problem model is after I think it's sort of US English slang for these gambling machines. They're called one-armed bandits. They have one arm because you pull it to spin the reels, and they're bandits because they steal all your money. And the analogy here is supposed to be to any kind of decision that somebody might face where there's uncertainty about their options. So here we have a scientist. You know she's a scientist because she's wearing glasses, and she's confronting two of these options. She can choose to either play the black or the red bandit, but she initially doesn't know what is the payoff of them. So she doesn't know which is the better thing to do. So she has to learn by trying. So she might start off by playing the black bandit, and it pays her 4. The number here can be anything. This could be dollars, it could be epistemic value, it could be anything. We'll just use a number to represent how good something is. And she doesn't know, is 4 good or bad, because she doesn't have any sort of comparison. So she has to try out the red bandit, maybe it pays her 3. She thinks, okay, that's not as good as the black one. She goes back to play it. Maybe it doesn't do as well, it only pays her 1, so she goes back to the red. And this process goes on and on and on. So she can continue this process by making decisions about which option to play. Her ultimate goal is to maximize her total payoff. So this is an old statistical model. It goes back until at least the 1950s, where it was used as a model for assigning people in medical trials, where the goal is to try and both learn about which treatments are more effective, but also minimize the number of people that are subjected to the inferior treatment. But it can be used to model lots of different things. So for instance, it is an effective model about any situation where we might lock in. That is, where we mistakenly abandon something that was superior in favor of an inferior option. So the reason that I'm using it is precisely because it's an effective model for studying the phenomena that Kitcher, Hull, and Zollman were thinking about, which is the possibility that we might abandon a superior theory and lock in on an inferior one. So bandit problems are one way of modeling that. It also models something that in economics and psychology gets called the explore-exploit trade-off. That is, the trade-off between exploring your options, trying out different bandits that might be better or worse, but also taking advantage of the information you have, exploiting the information you have in order to try and do the best you can. The thing that makes it slightly different than the sort of classic model in philosophy of science is rather than thinking about evidence as just simply arriving, and the scientist is a passive observer of evidence, the scientist themselves has to actively generate evidence. They have to choose which bandit to play, and so whether or not they converge to the correct answer depends on their individual choices. And their choices in turn depend on their beliefs. So if they decide that one arm is better and so they should just play that, then they will only get information about that arm, and they won't get information about the other one. So it changes the traditional model in philosophy of science by, instead of thinking about passivity, the agent now is an active part of the system for generating evidence. Evidence is generated by the agent and depends on the agent's beliefs in a way that is slightly different than the classic model. I think that this is an important shift because this is a model, it's not the only one, but it's a model which allows us to articulate exactly the concern that Kitcher, Hull, and Zollman had in mind. That is, we might abandon something superior in favor of something inferior. So that's why I chose it here. It's not that I think it's the right model for every problem, but I think it's the right model for this problem. Okay, so what all does this represent? So the agent, the person who's playing the slot machines, represents a single scientist or a lab, a single scientific actor. That is, an actor which we can think of as having a collection of beliefs and making a collection of choices. The bandit here represents something like a theory, a methodology, or a piece of experimental equipment. That is something which has a competitor and something which might be better or worse than the competitor, but where we can only learn by trying. An individual pull, that is an individual play of one of the bandits, represents an attempt to apply the theory or the method or the equipment to a particular problem. So in the context of, say, somebody like Zollman, the bandits are the plate tectonic theory or the unmovable continents theory. And those are the two options. And then one individual pull is an attempt to apply that theoretical apparatus to answer some particular quandary. So if we want to know why does the coast of South America look like the coast of Africa, that would be a case where the continental drift theory would be superior. But if we want to know what's the physical mechanism for the drift of the continents, at least at a certain time, that might be a failure. And that might be a case where the immovable continents theory is superior. The payoff represents how well the theory, method, equipment does at generating useful knowledge. So we can think of low payoffs as being something like a failure, right? We try and apply the theory, it doesn't give us anything interesting. It fails to explain something, it fails to predict, the equipment breaks, it doesn't give us a reliable result. High payoffs mean something like success. We've used the theory to learn something new, to generate a new explanation, something along those lines. And then we have to ask how the agent makes a decision. That is, how does the agent decide which method to apply? And that's going to be our next topic, which is how do we want to model our agents as making a decision in this context? In order to answer that, we have to first specify an underlying precise version of the learning problem. And so what I'm going to do is rely on this particular precisification. The results that I'm going to report don't really depend on it. This just makes things a little bit simpler for our discussion. So what we're going to assume is we're going to assume that one bandit always pays off exactly the same amount. The agent doesn't know this antecedently. So this is God's eye perspective. We, the modeler, know this, but the agent doesn't know this. One bandit is always going to pay 0. Right? And 0 is meaningless here, so just some number. Doesn't really matter that it's 0. 0. The other bandit is more uncertain. So the other one pays a draw from a normal distribution, which is better on average than the other one, but the agent doesn't know that. So it turns out the red one is better than the black one. It's drawn from a normal distribution and will allow the normal distribution's variance to change. And that will be our way of representing the difficulty of the problem. So if the normal distribution's variance is very small, it's a very easy problem because most of the time the red bandit will pay better than the black bandit, and so the agent will very quickly learn that the red is better than black. If the variance is very large, it's a very difficult problem because although on average the red bandit will be better than the black one, a lot of the time it will appear inferior. So high variance make the problem difficult, small variance makes the problem easy. Okay, so how should the agent choose? Well, there are lots and lots and lots of algorithms that one can think about for bandit problems. It's been an area in machine learning now for some time, but before that statistics, psychology, social psychology. So there's an enormous panoply of potential options. I've taken 4 here and ordered them sort of in terms of what we might think of as their sophistication. The stupidest, and genuinely quite dumb, is to just completely choose at random. So flip a fair coin, play one, flip a fair coin, play the other. This is to explore only and never exploit. So why is this dumb? The agent will, in the long run, be certain to learn which bandit is better, in fact. So that's the upside of it. She's definitely certain to learn which is the better option in the infinite limit. But she doesn't take advantage of that information. So she doesn't do good for herself because she's choosing at random. The sort of next level of sophistication is what's often called myopic optimization or greedy approaches. These are where the agent just looks at what she's seen so far, chooses the option that appears superior, and then goes with that. So she's myopic because she never explores. She only ever exploits. She looks at the information she has available to her and she chooses the option which is superior. The next level of sophistication is what are called epsilon greedy approaches. Here our agent has a parameter, epsilon, which determines the rate at which she explores. So with probability 1 minus epsilon, she's greedy. She does the thing that looks best. And with probability epsilon, she chooses something at random. In our case, just flips a coin to decide what. So the higher the epsilon, the more she explores. The lower the epsilon, the less she explores. So this is a simple way to represent exploratory strategies. The most sophisticated would be a full Bayesian utility maximizing agent who has beliefs over the distributions of the various bandits, updates those using Bayesian reasoning, calculates the expected utility for the entire history of play of each of her options and maximizes according to that. Those are so complicated that in fact we don't even have closed form representations of them for arbitrary bandits. We only have them for specific assumptions about the structures of the bandits. And there are a couple of variations that closely approximate it. Thompson sampling is one. There are a few others that get very close to it. But for our purposes, I'm going to focus on the simpler one, the epsilon greedy approaches. I do this for 2 reasons. Experiments on humans suggest that humans don't approach the fully rational solution. Epsilon greedy does okay, but not great at predicting humans. In fact, this is one of those cases where every paper you read says a different model best approximate human reasoning. Epsilon greedy often never wins, but is often second in all of these. And so I'm choosing it as a sort of compromise between the various debates about what is the best approximation of human reasoning. The second reason is it's very simple. It's a 1-parameter model. And so as a result, it allows us to explore the space of possibilities relatively easily without having to worry about these other models, which are oftentimes multiple parameters, large dimensions, which we would have to analyze. The second thing is, how are we going to measure our agent's success? One thing we could do is just ignore their payoff and just ask whether they converge in the long run. That's what I did in my early research. If you're familiar with my early papers from the late 2000s, early 2010s. That's what I did. I've shifted, and now I'm going to use maximizing their average payoff. Some of the results change very slightly, but the qualitative results don't, and I just prefer this for interpretive reasons. So I've made that shift. So first, let's talk about what's the best epsilon for our agent. So we're imagining still just one agent. We haven't gotten social quite yet, who's confronting one of these bandit problems. And we might ask, what is the degree of experimentation that would be optimal for her? And the answer to this question actually depends on how difficult the problem is. So what this graph shows on the x-axis is the epsilon of the agent. It can range from 0, meaning she never explores, she only exploits, to 1, meaning she only explores and never exploits. The different lines represent a different degree of difficulty for the bandit. So the black line is the easiest, the brown line is the next, the blue is the next, the gray is the next, and the red is the next. And you can see, correspondingly, that as the bandit gets harder, the agent performs worse kind of no matter what. And that's no surprise. If I give you a harder learning problem, it will mean that you don't do as well at it. That's what it means to be harder. The stars, which are a little hard to see here, I don't know if you can see my, yeah. So the star, there's a 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 star. They illustrate that as the problem becomes more difficult, the agent should explore more frequently. The optimal epsilon increases as the problem becomes more difficult. So in the most extremely difficult problem that I consider here, the best thing for our agent to do is assign an epsilon around 0.3, 0.4 in that range. Okay. So that's what we see here, that as it becomes more difficult, the agent should explore more precisely to avoid that problem of lock-in. Because the problem is very hard, she might get very misleading results, and because she might get very misleading results, she should explore a lot in order to make sure that she doesn't lock in on the inferior theory. Okay. Now let's shift to communities, because that's really where Zollman and Hall and Kitcher's argument is being made. Not that an individual will be better alone when she's biased. In fact, that's almost a contradiction, right? What it is to be biased is to be worse. Instead, their argument is a community is made better when the community features people who are biased in it. And so now we need to think about how we adapt this model to communities. So what we're going to assume is that all of the agents are playing the same bandit problem. So that is, they're all confronting the same two options, and the options on average pay off the same for all the agents. So there's no notion of like, I'm better at one or you're better at the other. There's no notion of we're actually asking slightly different problems. We're asking exactly the same problem. We're doing the same thing. But when I play the red bandit, I get one payoff, and you might get another because they're random. But that's the only thing. It's just random variation. Everything is, in the language of stochastic processes, independent and identically distributed. So my payoff doesn't affect your payoff in any direct way. It just provides evidence for which is the more superior bandit, which is the better bandit. Everyone can observe the results of others, although we're going to allow that observation to be structured in a social network. So what it means to be connected in the social network is those are the other person's results that you can observe. So if we're looking at this agent here, say, they can see the results of this agent, but they can't see the result of the agent on the far right. That is, they're not connected in the social network, so as a result, they can't see one another's results. All right? Critically, we'll impose one additional notion of boundedness, which is if I can observe Katerina, then I can observe her play and I can observe her results. But I don't try and infer what somebody who she sees is doing. So I don't try and watch Katerina's choices and try and infer, oh, I know she talks to Jacob, and so maybe I can infer what Jacob's been doing and what his payoffs are from her behavior. So I just treat her results as the only results that are there. I'm not trying to guess at what's happening with people I don't see. So what we're going to do as a first analysis, now we haven't introduced bias yet, but just to get a sense for how these communities work, we're going to imagine a community that starts off with what's called a minimally connected network. So the dark lines here represent a minimally connected network. So that is where there's a path from everyone to everyone else, but there are no more connections than necessary to do that. So very sparse social situation. And then we'll also imagine that we could add edges at random with some proportion p. And so that will allow us to go from a very disconnected society to a very highly connected society without worrying about our society sort of breaking down into multiple different societies. So now here's a very complicated graph, but don't panic, I'll walk you through it. The x-axis is that value p. So the x-axis is how connected is our society. So on the far left is not disconnected, but minimally connected society. So it's as connected as it could, it's as unconnected as it could be while still being a single society. On the far right, on the x-axis, is completely connected. Everybody observes the results of everybody else. Okay. Each individual line that I've put up here is for a different epsilon. So we have a community of individuals, each of whom has the same epsilon as everyone else. And each line represents a different potential epsilon. In fact, each size of the dot represents a different epsilon. Let me just have you focus for a minute on the solid black line on the bottom. Those are the agents who don't experiment at all. So these are the agents who simply do whatever looks best. They're the myopic agents. Those of you that are familiar with my earliest work on this, that is the analysis that I did, right? Was focusing exclusively on myopic agents. And you see that in this setting, it's good for the community to have very little connection, right? In fact, it's best for it to be almost minimally connected. So the ideal community in that setting is for it to be connected to a relatively small degree, about 20%. More connected than minimally connected. More connection gets worse. Why? Well, precisely for the reasons that we've been talking about all along. The more connected the society, the more likely the bad result will convince all of us to abandon a superior theory. And once we've abandoned it, we never go back. Because if we all see the same evidence, we all respond to it identically. And so we eventually ignore it. We don't have sufficient diversity in the community. One way to increase diversity is to make people experiment more. And so we see here that these other epsilons do quite a bit better. But a general pattern emerges. As we make people experiment more, they can tolerate and in fact benefit from more connectivity, but they never want to be fully connected. Right? So nowhere in here is it that the fully connected network is best. So every single one of these lines, except for this one, and it's hard to see, but in fact, even not that one, the best community is less than fully connected. So even when we make individuals engage in experimentation, that's good. It makes them explore more, but still, it's not the best. And in fact, the absolute best community, it's a little hard to see on the graph, but it turns out the absolute best community has a very small epsilon, 0.004, and is about half as connected as it could be. Right, so that would be the best community. If I knew everybody was playing this strategy and I was a god of science, what I would like to do is make people experiment about 4 out of 100 times and have them communicate about 40% of the time. That would be the best thing. Okay? Why? Because both epsilon and limiting information helps to preserve diversity in the community. It helps to make sure that we don't abandon the superior theory too early. But it also helps to ensure that we don't experiment too much. Because of course we could just set epsilon to 1. That would be the totally random strategy. That would make sure that we never abandon the superior theory, but it would also mean that we hold on to the inferior one forever. We would still have people who thought continental drift was false, for instance. Okay, so what's going on here is that there's a single underlying value, diversity of behavior, experimentation. Epsilon is one way to achieve that. Limiting information is another. One can have too little or too much of that. And so there's a sort of Goldilocks zone that we're trying to hit. And that the way we hit that is each thing gets added in a different way. And so we maximize our community's chances of success by doing a little bit of each. Okay, but so far we haven't said anything about bias. So now that we have a model which can formally represent the idea that Kitcher and Zollman and Hull had in mind, let's return to that by introducing bias into our model. Now, unfortunately, Hull especially, but also to a lesser extent Kitcher and Zollman are a little unclear what they mean by bias. Hull is notoriously unclear. And so I want to divide it into 3 different categories, and I'm going to look at one which is, I think, the best case for especially Hull, but for all of them. The first kind of bias is just outright fraud. Right? I just make up results because they're good for me. And we could model that. And in fact, Bennett and Justin have modeled it in this paper of the problem of intrinsically biased agents. Great paper. We're not going to go in that direction, not because it's the wrong direction, but because I think that this is going to be the worst case for Hull to begin with. So we're trying to do the best case here. The second is something more like borderline fraud. So this is now being called these days questionable research practices, QRPs. So things like p-hacking, or maybe adopting unknowingly adopting inferior methodology. So these are things where maybe the agent themselves doesn't know that they're biased, but they're nonetheless biased sort of by accident or something like that. Bennett and Justin also consider that in this paper called Experimentation by Industrial Selection, also could be modeled in this framework, and they do there as well. The thing I'm going to consider is what I'm calling file drawer bias, which is, I think, also quite familiar. The idea here is no individual published experiment is false. Every experiment is true, but we have agents who don't publish everything they do, right? So they have an opinion, they're trying to convince others of that opinion, and so if they have a result which suggests against the thing that they prefer, they take that result and they put it in their file drawer. They don't publish it. So that no study is fraudulent, no study is manipulated, but not all of their data is published. Right? And this is a real thing. It's well known. There's lots of evidence that this is happening in science. And so it's also quite plausible type of bias to be concerned with. Okay, so that's going to be our focus, file drawer bias. And this is related to something called the tobacco strategy, which was first discussed by Oreskes and Conway in their really excellent 2011 book, Merchants of Doubt, and then modeled again in this framework by Jim Weatherall, Kalen O'Connor, and Justin Bruner in this paper, How to Beat Science and Influence People. That the tobacco companies were sort of doing a version of the file drawer bias, not in science itself, but in the relationship between science and policymakers. So they would take scientific results and only show them selectively to policymakers. What I'm doing that's different than what Jim, Kalen, and Justin did is thinking about how this affects science itself rather than affects the science policy interface. So rather than thinking about the tobacco companies as doing this with respect to policymakers, I'm imagining what happens if scientists do it themselves, internally within science. So I'm going to imagine we have a community that's made up of two types of people. Unbiased agents, exactly like the agents we had before. They publish all their results to their network neighbors. They update based on all the evidence they received. But the one thing is they're not attempting to correct for file drawer bias. They're just looking at the evidence they see and updating on it as if that's the entirety of the evidence. This is, in fact, there's pretty clear empirical evidence that although scientists kind of know they shouldn't be doing this, they don't. This is in fact what they do. They mostly treat the published results as if it's all the evidence that's there, except for when they're in sort of a more sophisticated mood. The other type of agents are biased agents. So they have a preferred bandit. They either like the red bandit or the black bandit. That's determined at random. Where the results suggest that their preferred bandit is better, they publish those. So if the preferred bandit outperforms the dispreferred one, or the dispreferred one underperforms the preferred one, they publish those. But anything else is left in the file drawer. So they don't publish those. They don't share those with those network neighbors. Right? So every result that they show to their neighbors is a real result, but they just choose not to show all their results to everyone. They keep quiet. Okay. So now we can ask. We now have a formal model which is very easily analyzable. So let's imagine that we have a community, again, structured in exactly the way I described before, minimally connected graph with potential additional connections. So that's, again, the x-axis. The y-axis is the performance of the community. Higher numbers mean they do better. Lower numbers mean they do worse. And the different lines are what proportion of the community is biased. So how many of our agents are biased? So the black line is the same line that I showed you before. That's a community where we have no biased agents. And so that's our sort of baseline. The thing to see very quickly is that bias is pretty good in this community, right? It's not absolutely always better. There are some times where the dotted lines dip below the solid lines. But if I'm God of science and I get to design my community, I would like to have a very well-connected community with biased agents in it. That's the ideal, right? These are the best, clearly, with some relatively large number of biased agents in them. Why is that? Well, it's because the biases, let me add one other thing. Notice these are all even numbers, 20, 40, 60, 80%, and that's because we're considering a community of 10 people, and we're making sure that we have agents biased in both directions. So if we have 20% of the community is biased, that means we have one agent is biased in favor of one option and one agent is biased in favor of the other. And this is critical. Why? Because our biased agents are doing what epsilon was doing for us before. They're doing the exploration for us. So if I'm biased toward the black bandit, I'm going to try and convince you that the black bandit is better no matter what. And if you're and you're biased towards the red bandit, you're going to try and convince everyone that the red bandit is better no matter what. And together we balance each other out, and our biases actually are informative to the community. because the results that you won't publish, I will, and vice versa. And so as a result, we actually generate really good information for the rest of the community, and the community who's unbiased, the unbiased agents, are benefited by the presence of the biased agents. So this is, I think, the best case scenario. This is sort of saying Hull definitely could be right, that our community does better because of the presence of the biased agents. Right? So this is sort of optimistic result for Hull. Now let's explore how robust this result is. That is, what if we change some of the assumptions that I mentioned? Okay? So the good news is Hull is right when biased is equally distributed and social location randomly determined. I didn't mention that, but who is biased is just also chosen at random. It functions very effectively to preserve diversity. But what about the bad news? Well, now let's imagine, first let's just consider two very simple networks. One is the ring network that's on the top, or sorry, it's labeled cycle there, but it's a ring network. And the other one is the complete network, where everyone's connected to everybody. Now, let's imagine that we have only one biased agent in our community. Or sorry, only one type of biased agent in our community. Let me rephrase that. The number can vary, but they're always either biased towards the better option, or they're always biased towards the worse option. The solid lines are when they're biased towards the better option. No surprise. If we could be biased towards the truth, we'd like to be biased towards the truth. I mean, it's not even really bias anymore, right? That's just being right. So we do better when we have a community where people are constantly trying to convince us of the truth, and they're doing so even at the cost of maybe not giving us all the information. But that's great, because they already know the truth, or at least they're pointed in the right direction. Now, what if we only have people that are biased in the wrong direction? These are people that are biased towards the falsehood. Well, now things can get quite bad, right? And here I want to point out one thing about the scale here. So 0 is the worst you could possibly do in the bandit problem as I made it, right? If you started out choosing the worst option and stuck with it no matter what, you would get a payoff of 0 on average. So in a community where 40% of the people are biased towards the truth, and where people don't communicate that often, we're doing almost at the theoretic worst that we could possibly do. And 10 is the best you could do. So if we have a community of people that are only biased in one direction, we can range from almost the worst that we could possibly do to almost the best we could possibly do. So it really matters what type of bias exists in this community. The other thing that really matters is social location. So now we can imagine that instead of starting out with a minimally connected network, we start out with the star graph. So the star graph has one person in the center and everyone connected on the outside. And what we're going to do is we're going to make the person in the middle biased. So that is the person whose bias now is the most socially connected person in the community. They're the central hub of the community. When that person is biased, they can really ruin things, even if their bias is randomly determined. So here is the red line there on the bottom is the center person is biased and no one else in the community is biased. And they can actually make the community do quite badly because their bias basically determines what happens in the community because no one else talks to anyone else. So they talk very little to each other. If you have somebody who's biased in the other direction, who's on the periphery of the social network, then initially, sorry, ignore that for a moment. Initially, it doesn't matter because one person on the periphery who's biased in the other direction doesn't matter because they don't talk to anybody. But as the connections increase, then the community does a little bit better. Let's not worry about that for the moment. Okay, so what's the bad news here? So the good news is that when bias is equally distributed and social location is randomly determined, bias can very effectively preserve diversity. However, when bias only goes in one direction, or when the person who's biased is systematically over-influential in the community, that is, they're more influential than the other people, things can be very bad. Right? In fact, they can be almost as bad as possible. So let me stop there for a second. I'll come back to this in a second, but let me stop there and say something about what we should conclude, both about the independence thesis and about David Hull, Miriam Zollman, and Philip Kitcher. So Hull says that science could be made more progressive through bias and irrationality. And we've shown that that's true, right? If biases are about equally distributed, and social location is determined at random, then our community could be almost as good as possible if we had biased agents in it. So he's right. We have constructed a community that is made better by bias. But he's also wrong, because if we don't do that, if we have bias going only in the wrong direction, or if we have the biased agent being overly socially influential, then we've made the community far worse by having biased agents than it would have been without them. And so we've also shown that Hall is wrong. So have we shown that the independence thesis is true or false? Well, I think we've shown that it's true because we've constructed an example where it's true. That is, where making individuals irrational made the community better. But that doesn't necessarily translate into a policy prescription because it doesn't necessarily say that all ways of making the agents biased or all potential interventions would make the community better. So it suggests the independence thesis is true in maybe a really strong sense. Bias can be both good and bad, and whether the community is made better by bias depends a lot on ancillary questions, like how many agents there are, what are their various proportions, and what is their social location. Okay. Now, I promised that I would take a step back and talk a little bit about computational methods and using this as an example. And so I would like to just do that here for a second. Because a computational philosophy, while gaining in popularity, is still, I think, a relatively new and controversial way of thinking about doing philosophy, even though computational methods have really taken off in other sciences like physics, chemistry, and to a maybe lesser extent, but still significant in the social sciences. The first reaction that many philosophers especially, but people often react when they see a model is the model has false assumptions, right? It doesn't look like a deductive, a sound and valid deductive argument, right? I've made a bunch of premises that are false. People don't really use epsilon greedy. We don't know what they use, but probably it's not exactly epsilon greedy. They might vary in terms of their strategies. They might be better and worse at various bandits. There might be more than two. They communicate in various complex ways, not in the simple way I represented. We could go on and on and on. There are hundreds probably of false assumptions in the model. But when you're thinking about a model, it's not about whether the assumptions are true or false. And then here I have a picture of Borges. Borges has this micro story, like it's literally like 5 sentences long, about a king who asked his cartographer to draw a full-scale map of his territory. And Borges called this story On Exactness in the Sciences, or at least that's the English translation. And the idea was, this is ridiculous. An exact map that's scaled 1 for the territory is useless because it's just the territory. And so we always have to make false assumptions, simplifying assumptions, in order to help us better understand. So the question is not whether there are true or false assumptions, but rather whether the model is fit for purpose. Are the details that are being left out relevant for our conclusions, yes or no? Just like when you ask about a map, is the map fit for purpose? You ask whether the details that it left out are relevant or not. So your Google Maps doesn't give you, doesn't tell you, say, a height above sea level. Maybe you don't care, but if you're an airline pilot, you don't want to use Google Maps because you want to know height above sea level, so you don't crash into a mountain. Okay, so the precisification of this question for our topic here is, would making the model more realistic render the independence thesis false? So that is, if we replaced one of my false assumptions, or many of my false assumptions, with more true assumptions, would that suddenly make the independence thesis false when it was true before? And I conjecture that it wouldn't, that a lot of the details that I left out don't matter for the purposes of my argument. But that's just a conjecture. I could be wrong about that, and that's something that the process of modeling can help to find out. We can consider different variations on the model. We can consider whether we adapted the model in different ways, whether the independence thesis would be true or false. But it's a conjecture. Now, Connor and I argued in a different paper, this paper, about whether or not philosophy, we should see models as philosophy, that models share a lot in structure with thought experiments. And so this is in other of Zollman's work. She uses a more thought experiment-like methodology in her book Social Empiricism, where she considers potential, what if the history of science had been different, and let's imagine what would have happened if the science had progressed differently. Hull does this a little bit less, although it's still there, maybe. But the problem with thought experiments, especially in the social realm, is that it's very easy to make mistakes because it's very hard to imagine how social processes will unfold in our minds. Social processes are complicated, and they involve many interacting parts. We're not always great at thinking about complex systems in that way. And so one of the virtues of using computer simulations in this context is that they force precisification of exactly what our assumptions are and exactly how the system works. That precisification comes with a cost, of course. It means that we have to make idealizing assumptions. But like other modelers have argued before me, I think we're all doing that, even when we do thought experiments. We're just not explicit about them. And so the virtue of computational philosophy is that it forces us to be explicit about what our assumptions are in our thought experiments rather than ambiguous, which is how our thought experiments normally proceed. I also think that they have a similarity to something that gets called bench testing in engineering, which is that you might take a system, like a complex engineering system like a car, and you might give it a simple task to determine how it behaves in a complex environment. So you might put it on a dynamo and drive for a little while to see how the car reacts to, say, various accelerations and decelerations. That, of course, is, in a sense, a false assumption because cars don't drive on dynamos. They drive on roads. But we put them on dynamos because we want to control everything except for acceleration and deceleration, because we want to know how that affects the system as a whole. And I think that that's a lot of what the motivation for doing modeling is. So in this particular case, I wanted to know, can bias help out science? And so I wanted to take a simple model where the only thing I manipulated was whether agents were biased or not, and where their social location was, and then hold everything else sort of constant. Now, of course, we have to hold it constant in a particular way, and maybe that's the wrong way, but it's allowing us to isolate one potential cause, bias, from the others, which is something we can't do if we use principally historical data, because, of course, we can compare systematics in biology to DNA, to physics, but there are many things varying there. It's not like a bench test, but rather has the complexity of the real world. And in fact, I also think that there's an analogy to lab experiments on humans. So here I have a picture of really, I think, quite ingenious, actually, experiment that's done on human beings about vision, so about psychology of vision. So the idea is that you bring a person into a room. This is a real room, not a computer screen. I mean, obviously, this is a computer screen, but the experimental subjects are in a real room, looking at two real objects. But the objects have been manipulated. So the lighting gets changed. The objects can be rotated. They cannot be rotated, but they can be made to look like they've been rotated. So they might, in fact, be looking you head on, but being an oblong shape that makes it look like they're rotated. And the experimental procedure is varied in terms of lighting and various things to try and figure out how our vision system determines whether an object has been rotated or whether it's an oblong shape. And so the subjects are put in, they're shown something, they're then asked to choose which object is rotated and which object is not rotated. They measure how long it takes the subjects to do that and whether they're right or wrong, and then gives them feedback potentially on that, and then it's continued. Now, we could look at this psychological experiment and say, this is very unrealistic. No one is ever looking at little pedestals with disks that have been manipulated in an artificially controlled lighting environment. There are lots of false assumptions in this model of human vision. But nonetheless, we sort of think, well, but we can learn something from it, because there's an analogy here between how we look at objects in this system and how we look at objects in the real world. And so I think that the analogy here is that both in the context of modeling and in the context of experiments on humans, there's an inductive gap where we have to move from the lab to reality, or we have to move from the model to reality. And one can legitimately ask whether that gap can be spanned or not. And one can do it in laboratory experiments, and one can do it in models as well. And so this is a good question. One should ask this question. Does my model represent reality well or not? But that question is not a question that's unique to modeling, but is a question about any kind of analogical reasoning that we do in science, which is quite common. So my argument is that in all of these cases, whether it's the thought experiment, the map, the experiment on humans, or the bench test, we have to make an inductive leap. And so whether or not we think that that's a problem for modeling, it's not a problem for modeling, it's a problem for all of our science. And it might be that a particular model doesn't span that inductive gap, just as a particular experiment might not. But it's not as though models are obliged to a higher standard just in virtue of being models, because laboratory experiments are models too. They're just a different kind of model. Okay. So what I think that I've shown is that models, especially in this context, my model, is a proof of possibility. So what my model has shown is that the independence thesis could be true in the idealized world of the model. And I think that that is uncontroversial. Right? The independence thesis is true in the idealized world of the model. The next step, to say whether the independence thesis is true in our real world, or at least could be true in our real world, involves an inductive leap. We have to ask whether or not the true statement that we made about the model is representative of the true world. And that is a leap, right? That is a leap that we have to make. We have to make it on the basis of other evidence that we have. Do we think that the model is representative in the right ways? Yes or no. Do we think that it provides a good analogy for real social systems? Yes or no. I think it does, and I'm happy to talk about why I think it does. But of course you might react differently, right? I'm not saying one has to make that inductive leap. That this is exactly the kind of thing that, just like in any science, is part of a process of discovery. And so as we learn more about models and we learn more about people, we might discover that there's a bigger gap than we thought. And maybe we shouldn't have made the inductive leap that we did, or maybe we were smart to not make it. And so rather we should see modeling, and like all of science, as part of a process, not the end of it. So it's not like I've given you a deductively valid argument that the independence thesis is true. I don't think I could. I won't even try to. But rather I think I've given you some inductive evidence to think that the independence thesis is true in the real world, just as it's true in the individual model. Okay, so let me just wrap up here. We're sort of just at the end of time. So I think that I've argued that the independence thesis is true. Zollman, Hull, Kitcher were right in a sense. That is that science can be made better through the biases of individual agents. Not just that it can be good despite it, but rather it can be good because of it. However, as a tool for making science better, it's an extremely dangerous tool. Because just as bias can make science better, it can make it worse, and it can make it almost as bad as we could fathom. Right? In the model, as bad as it's possible. And so as a social tool, Hull seems to almost champion it. It's quite dangerous, and it's something that we shouldn't strive for. So if we find out that our scientists are biased, we can't make the conclusion that the sociologists made, that science as a whole is irrational. But on the other hand, it's not like we should run out and tell the scientist, boy, it would be really good if you were more biased. Please be more biased, right? Because we could really screw things up by doing that as well. So it's a cautionary truth of the independence thesis, but a truth nonetheless. And I think that it's understanding this is something which is really only possible through computational modeling. And so while computational modeling doesn't answer every question that we could ask, this particular question is really ripe for computational models. And I hope my computational model has convinced you that there might be other problems as well that might be useful to be answered in this way. All right, thank you very much.